Welcome to my presentation on security for connected automated vehicles, where I will focus on a special part of automated driving, cooperative adaptive cruise control, and also report about other activities in this field that we investigate as part of the SecForCARs project, which is a German national funded project. I'm Prof. Kargl, I'm from Ulm University, and I'm involved in security for automotive systems for, I would say, more than 15 years now. And well, we started looking into communication. Recently, the focus shifted more towards automated driving. Still, if we look back in history, what was realized throughout the 2000s was that cars get more and more complicated in their electronics architectures. You have dozens of electronic control units connected by various types of automotive networks. And what was neglected when originally designing these systems was security. That is, nobody asked the question, what would happen if an attacker maliciously tries to infiltrate the system? And this apparently became a problem throughout the 2000s when cars started to become networked, either through cellular networks or, for example, also the then upcoming car-to-car communication. And this led to a whole series of research into the security of automotive systems. And there were analysis done, for example, here by people from University of Seattle and others who hacked a car that was Chekhoveh et al. Karl. There was investigations into, for example, the communication unit of BMW systems or BMW cars, and there was the research of Charlie Miller, Chris Walasek, which basically all showed that our systems, our automotive systems, were not appropriately secured. One could even say not secured at all, and that this needed to be changed, in particular if you wanted to have connected cars. Myself, I was involved in a whole series of projects over the years, starting in the mid-2000s with the European project CEVECOM, which pioneered many things or many parts of the security architecture for car-to-X communication that you find in the European standards these days. But of course, we also collaborated with other parts of the world, in particular with the US and IEEE. The Preciosa project focused on privacy aspects of connected driving. And then there were other projects like Converge, Preserve, where we tried to prototype a full car-to-X security subsystem, including a dedicated and specialized hardware security module, where we built first an FPGA and then an ASIC version of it to, for example, accelerate cryptography, but also protect key material in a car, etc. And I will then later focus a little bit more on what we are doing these days in the SecForCARs project, where we take the step beyond just looking at the communication system and also focus on what is particular from a security perspective about a connected and automated car. Over these years, when someone asks me, what do you need to do to secure a connected vehicle? I always showed this slide here where I argue, well, you need three basic building blocks. First, you need some form of identity management, integrity protection for your communication. In essence, you want to ensure that only valid vehicles with valid credentials can participate in ITS communication. And if you have the typical roadside attacker with a laptop that wants to manipulate the ITS system, that would not work, because that roadside attacker with a laptop would not have valid credentials to do so. Yeah, this basically means you issue some sort of certificates to vehicles, you sign your message, you digitally sign your messages. Yeah, and you face a couple of scalability problems here, but this is, I would say, well understood and mostly resolved. Next, you have to ask the question, now that vehicles start communicating their position, their speed, their heading to everyone in the vicinity, and maybe even to backend systems, there's the risk that this data is abused to track vehicles and drivers. So you have a privacy issue. How do you solve that? And a lot of work went into investigating how, for example, changing pseudonyms can be used to allow better privacy protection once these systems are used in the field and in practice. Yeah, and then there is this third building block, which I would say is the least understood of the three. Also a lot of research happened there, which we call misbehavior detection. And yeah, in essence, it's about the question, how do you prevent a valid vehicle that has credentials, yeah, and can therefore send legitimate messages to other vehicles? How do you prevent such a vehicle, if it's maliciously manipulated, to send incorrect data and then manipulate, for example, automated driving functions in the end? Yeah. So this question, how do you make sure that vehicles only rely on authentic and correct information that they receive from other vehicles, but don't fall prey to spoofed and incorrect information? This is something that also has quite some history, and the earliest works date back like 15 to 20 years now already. And in essence, we here ask not the question, how do we keep external attackers out of the system, because we assume that our credentials, our certificates, our digital signatures do that, so that really only cars communicate among each other. But here we ask a much harder question, how do we deal with insider attackers, that are part of the system, but that are malicious, and we actually don't want to consider the data they communicate in our driver warning systems or even in our automated driving systems. So we want basically also to exclude them from the network. Basically we want to teach our cars something that we humans do intuitively. We want to judge the trustworthiness of data we receive. And you do that every day. I mean, if I would now tell you, hey, look out of the window, there's a kangaroo there, and if you're not happen to be in Australia, then you would probably not even bother to move your head, because you would immediately judge this information to be totally unplausible. And this is exactly what misbehavior detection wants to teach to vehicles, to reason about the trustworthiness of information. And already some years back, we wrote a quite long article, survey article in IEEE Communication Surveys and Tutorials about misbehavior detection, cooperative intelligent transportation systems, where we try to compile all relevant literature in this field. And in this survey, we basically categorize the different mechanisms that were proposed in literature into different categories. On the one hand, we have node-centric mechanisms that basically try to judge whether a specific node, in our case a specific vehicle, can be trusted, for example, because it has valid credentials or it has built up a reputation to be trustworthy if we use some reputation system. Or we have mechanisms that look at the behavior, and if, for example, the vehicle triggers a flooding attack, for example, floods the network with data, then this can be detected, and then the node is not trustworthy. And then we have the second category of mechanisms that we term data-centric misbehavior detection mechanisms, which look not at the sender of an information, but rather at the data contained in the packets, the data itself, and either checks whether the data is plausible with some form of world model that is embedded into the mechanism, or whether it's consistent also with other information received, for example, from other cars. So let me give you a few examples of such mechanisms, and I will use only very, very basic and simple examples. You will later see that there are more complex ones, of course, too. Yeah, so let's start with node-centric trust-based mechanisms. So if some roadside attacker would send spoofed messages pretending that current speed at this position of the road is 0 kilometers per hour. So essentially this means there's a traffic jam, heavy congestion. But this message is sent with no certificate and no digital signature. Then you would not trust that message. You would not trust that sender. That's a very easy way to detect untrustworthy nodes. Regarding behavioral node-centric mechanisms, for example, this red car would start a flooding attack and flood the channel with messages. Then you would probably also detect this through some form of intrusion detection as an attack, and then you would also not trust the information coming from that node. On the data-centric side, I can also give you some examples. If, for example, this vehicle over here would send messages claiming to drive at 500 kilometers per hour, you could easily rate this information to be rather unplausible, because there are very, very few cars, even on German highways, that go at this speed, right? On the other hand, you could, for example, check consistency of data with information you receive from your local sensors. So if that vehicle, for example, would pretend to, in its communicated messages, pretend to be at standstill while your local radar tells you this vehicle is actually moving, you have an inconsistency, and this, again, can be considered a misbehavior. More challenging is the situation if a remote car at a remote position claims to be at a standstill. You don't have a local sensor like a radar that would tell you whether this is true or not. So you receive this information either directly or through multi-hop forwarding. But likely there will be information from other vehicles that are at the same situation or in the same traffic situation, and that, for example, then send also their speed, their position, ideally via node disjoint paths, so that this malicious car cannot filter this information out or modify it. In that case, this green vehicle will receive these two informations, and as the two cars are almost the same position, it can basically then maybe deduce that this is an inconsistency that has to be resolved before any of the two informations can be considered trustworthy. Okay, so this was just this categorization. Now, research in this field of misbehavior detection for ITS started, well, as said, in the early 2000s or mid 2000s, with a whole lot of proposals for individual single detection mechanisms. So when one early one that we proposed, the acceptance range threshold, would basically compare the claimed position in a message that you receive from a remote vehicle with its assumed sending range. And if you receive a message directly from a vehicle, that claims to be 2 kilometers away from you, then this acceptance range threshold would consider this message or this information to be, you could call it either inconsistent or unplausible. In any case, it would reject that information. Yeah, and research often then evaluated these detection mechanisms through through simulation-based studies. So, for example, we also did then a study where we looked at how such simple mechanisms perform, and you see that at least in this model, in this simulation, the detection rate is quite good at, let's say, a relatively low false positive rate. However, you also notice that different detection mechanisms work differently well in or against different attacks. And this is why in this case, we already combined the outputs of 2 of these detection mechanisms, so weighted averaging, also a very simple data fusion mechanism, you could argue. Yeah, and this was a general observation then, that there is no single detection mechanism that would perform well under all attacks. And therefore, people started to come up with frameworks that could embed more and more of these detection mechanisms. Yeah? And there's one example by researchers from TU Darmstadt and Opel, and they devised such a framework here. And I'm not going to go through the details here with you, but you see there are multiple layers of checks here that follow onto each other, involving Kalman filters to predict positions, and also Bayesian models to try to detect certain driving maneuvers, and so on and so on. Yeah, and as you can see, this becomes rather complex, and it becomes unflexible because it becomes harder and harder to add new mechanisms to that. Yeah, because the order in which you do the checks play an important role, and so on. And this observation led us to then propose a misbehavior detection framework called MART, where we want to have more flexibility in integrating many different detectors, switch some off, some on again. Yeah? And the core idea is that all information ends up that you receive from the outside ends up in a world model, and then you have all kind of detection mechanisms that would rate information, that would invest or analyze the information in the world model and provide their opinions on the trustworthiness of that data. And then you have a fusion mechanism that basically gathers or joins all these opinions together to have a final single outcome. And when I say opinion, I literally mean opinion in the sense of a special reasoning logic or probabilistic logic called subjective logic, which was originally developed at the University of Oslo, but has been applied in many different contexts where you want to reason under uncertainty. Yeah, and the core idea is that you can express opinions on statements or facts, and this is expressed, or such an opinion consists of a belief function, so you can express your belief in certain in certain values or information to be true or not, but you also have the possibility to express your uncertainty about this judgment in the opinion, and you also express the base rate, which basically means the probability of a certain fact to be true under or in absence of further evidence. Actually, this can be multi-valued parameters that you evaluate here, but for our purpose, we use a simplified version of subjective logic, which just uses binary domains, so a statement can either be true or false, but not have multiple values. This makes also the calculations easier, I would say. The nice thing about subjective logic is it brings along a lot of different fusion operators with which you then can combine the outputs expressed in these opinions of different detection mechanisms implemented in this framework. Yeah, and you have to choose the right fusion operators for the right information, or for the right to have the right semantics in different steps of this fusion. But there's let's say a sound framework, logic framework that you can resort to. I have a little bit more details about subjective logic, in particular for binary domains. There you can simplify the opinion to basically be a belief, a disbelief, and an uncertainty in a certain statement X. And these values range from 0 to 1, 1 meaning certainty, 0 meaning or meaning certain probability, 0 meaning no probability, and belief, disbelief, and uncertainty have to sum up. And in the end, you can project such an opinion on a single probability value. And to simplify it even more for these binary domains, you can kind of visualize an opinion, which is a precision inside this triangle of belief, disbelief, and uncertainty. And depending on where in this triangle you are, you either have more belief in the statement to be true, or disbelief, that is, you believe the statement is false. But the more you go up here, the more uncertain you are in your judgment. And if you end up here at this top peak, it basically means you don't have evidence beyond the base rate whether the statement is true or false. Here you are absolutely certain, so it's a Boolean true. You could say you're absolutely certain that the statement is true, no uncertainty. And here you're absolutely sure that the statement is false. Again, no uncertainty. And then, of course, opinions can be everywhere here in the middle. Yeah, and how MART works is now that you have these detectors, which can be node-centric or data-centric. They investigate the data in the world model, and they create opinions, for example, by checking if, for example, communication range is plausible or not. So this art detector I showed you earlier could be one of these data-centric detectors up here. And they will, and this art detector will then form an opinion on received messages. Yeah. The nice thing is that once you have many of these opinions in your world model, then you can use these fusion operators to come up to new conclusions, to new opinions. For example, if a node-centric detector has an opinion on a vehicle, and this vehicle holds an opinion on another vehicle, which holds an opinion on a data, you can use a transitivity to form an opinion over the data. And if you have multiple opinions on the same data, you can use so-called multi-source fusion operators to collapse this all into a single opinion. And in our research, we showed that this is a quite flexible and powerful instrument to do misbehavior detection in Car-to-X communication. But in the meanwhile, let's say the world developed further. People were not only looking into the security of communication and connected cars, but actually we realized that many of the assumptions that stemmed from the idea that you would use this Car-to-X communication for driver assistance systems, for driver warning systems, where you still have a driver that would make reasonable decisions, that many of these assumptions were not longer valid if you actually look into automated cars, where the driving reactions to received information would be automated, and where in the extreme case of level 4, level 5 driving, there would actually be no driver anymore that could influence the reaction of the car in the short term. And this, these challenges surrounding the security of communication and automation in cars led to the SecForCARs project, motivated the SecForCARs project, which is a German national funded project that involves a total of 14 organizations from academia and industry that together addresses a really broad spectrum of research challenges in connected automated driving. Our initial observation was and motivation was that an automated car has very complex data processing involved. So it uses a lot of local sensors, but also data received through communication to fuse this data and create what's called environmental perception. So a view of the neighboring world on which it then takes decisions. For example, it decides to drive right or drive left, and then at an intersection. And then, of course, you have to plan the precise trajectories and control the vehicle accordingly. And besides, of course, the vehicle also relies on local and external data sources like map, traffic information, and the like. And if you look at such a, of course, simplified architecture model of a self-driving car, then you can ask again the question, what are the attack vectors that a malicious attacker could exploit? Of course, the attacker can still manipulate the communication, like we saw earlier with when discussing misbehavior detection. But the attacker could also try to directly manipulate sensors. And in earlier works, we have shown, for example, how to manipulate LiDAR scanners to show fake obstacles. In SecForCARs, we are doing a lot of work in investigating the sensor security of radar-based systems and the like. So it's a viable threat that attackers manipulate the sensors input. Of course, also data sources may be compromised, and the attacker could also try to craft the data in a way that later the fusion and decision-making processes are manipulated, are affected. For our work on misbehavior detection, this step towards automated driving essentially meant that it's not sufficient anymore to just detect misbehavior and maybe filter the information out or warn the driver, but actually we have to go one step further towards misbehavior reaction. We also need to conclude what a car should do in reaction to a detected misbehavior, to a detected attack. And we did first analysis in this field already some years back, starting with looking into how effective attacks could be, and later then, and this is a paper from last year published at IEEE VNC, where we then looked into what strategies are available to react to such data falsification attacks. And we do this with a special automated driving function called CACC, or Cooperative Adaptive Cruise Control, which is a very simple form of automated driving. It's just about longitudinal control, but it involves both local sensors, radar sensors, but also communication. So this Cooperative Adaptive Cruise Control basically has the idea that is that vehicles form a platoon. You have a leader and you have followers, And the idea is that they should drive at an ideally perfect constant distance, and that this distance can be a lot shorter than, for example, with normal ACC, which only relies on radar sensors. Yeah, so this communication aspect gives you an additional advantage because as the data is explicitly communicated, there are no delays, for example, in learning when the car in front of you starts to brake, and this makes your platoon a lot more stable. Yeah? So the leader communicates its current speed and acceleration, deceleration position to the follower, and then so on. Yeah, and then, of course, from a security perspective, you ask the question, what would happen if a certain vehicle an attacker would manipulate its messages it sends to its followers in a way that it would, for example, signal an emergency brake. So it would send that it would decelerate at maximum possible deceleration while it would drive as normal. Yeah, and as a consequence, of course, this vehicle would then do also an emergency brake because it assumes this vehicle in front of it is braking. And we in an earlier paper from 2017, we could already show through simulation studies that current control algorithms, current CACC controllers, as they are called, they are not really equipped for this task to deal with this kind of incorrect information, and this can actually lead to crashes, and therefore you need some form of misbehavior detection to help the CACC controller to not fall victim to this manipulated information. Yeah? So instead of sending the data that you receive from the network or from the sensors directly to the CACC controller, which a normal CACC architecture would do, we rather send it through the misbehavior detection so that the misbehavior detection can rate this information regarding its trustworthiness. But then again, the question is, what would be the next step? What would be the reaction? And in our last year's paper, we then covered the whole design spectrum of how such reaction strategies could look like. And in this spectrum, on the one hand, you basically you try to run the controller completely unaltered, and instead have this misbehavior detection system just modify the input to the controller in a suitable way, for example, by adding noise or simply filtering out false messages. On the other hand, you can, of course, also try to get along without the misbehavior at all in the extreme case, by just making your control algorithm more resilient to these attacks. And then, of course, there are strategies kind of in between. And I want to talk now in the remainder of my presentation about one of these strategies in between, where the idea is that the misbehavior detection basically rates the information, adds a suspiciousness parameter as metadata to the information, and then we change the controller to take this suspiciousness parameter into consideration. That's basically the idea of this strategy I want to talk about. So, and we compare this with different other strategies that I can briefly outline next. So as information communicated within the platoon reaches the system, we first look into what's the baseline when we have no misbehavior detection and no modified controller at all. So that's kind of the maximum damage the attacker can create in absence of any security mechanism. We then investigate a strategy where basically the misbehavior detection detects the attack, and we assume it's doing its job perfectly in this analysis. So whenever you receive data from an attacker, misbehavior detection will immediately trigger an alarm, And this will make our vehicles change to or fall back to ACC, where it would not rely on any information from the network anymore, but just switch to sensor, radar-based adaptive cruise control. Next, we have this strategy that I was already mentioning with the suspiciousness parameter and adjusted controller reaction. So basically what the misbehavior detection would do when it detects an attack, it would rate the suspiciousness of the data in a probabilistic way, just between 0 and 1, and forward this information together with the data to the CACC controller. And then the CACC controller can take, depending on the driving situation and on the distance, for example, to other cars and speed, can take a decision whether to rely on this information or as an adjusted reaction to also then, for example, make the distances between cars larger or something like that. And that's strategy 3. And we ran quite a number of simulations in different driving situations of this CACC system. And I want to briefly show you the outcomes of that in these colored graphs here that I probably need to explain a little bit more in detail. So what you have here is basically on this x-axis the militia. So the platoon was is driving at a constant speed. So normally there would be no acceleration or deceleration reported, and now our attacker would report a wrong acceleration or deceleration of different strengths expressed here in meters per square second. And we did this analysis at different speeds and with these different strategies. So let's look at first at what's happening if the MDS misbehavior detection system is completely disabled. So in this case, the vehicles would, in some cases, if the spoofed information is not deviating too much from the truth, would continue driving at a certain distance. So this in these blue boxes, this number basically means the distance at which they continue to just drive stable in the platoon. For all these red boxes, you actually have a crash. So following vehicles crash into each other under this attack scenario, and the value expresses the speed at crash. So higher speeds, of course, means heavier crashes. And you see that even for mild deviations from the truth, like 3 meters per square second of deceleration, you already experience crashes, right? So just running the system without any form of security is obviously not a good idea. Then we have this fallback to ACC strategy. So as soon as the misbehavior detects there's something spooky going on here, something is fishy, we have attacks, it would immediately shut off the communication and fall back to ACC. And you see that it actually then kind of completely ignores the attacker, and it continues to form a stable platoon at certain distances. However, what you also notice is, depending of course on speed, these distances are a lot larger than the distances the system would drive at if there's no attack and no fallback to ACC. So you see this strategy is secure and safe, but it comes at a price that your platoons need more space on the road and drive less efficiently. So then we look at this strategy with the suspiciousness parameter, and we see that at least in a certain window here, even if there is an attack, the vehicle or the vehicles can still form a comparatively close platoon. So we don't need to fall back to ACC. Everything or the platoon stays rather compact. However, if the attack involves larger deviations from the ground truth, then we basically have a behavior that essentially includes or is essentially equivalent to fallback to ACC. Yeah, these decisions within this parameter-dependent reaction involves two thresholds that you can tune. So we also looked into how to tune them. Point being here that by tuning these parameters, you can enlarge this window where, despite of an attack, you benefit from CACC by having closer and tighter platoons. However, you also see that if you relax these thresholds too much, yeah, you will again have some forms of contacts and crashes between vehicles again. And we are currently in our ongoing work looking deeper into this relationship and behavior and also into these other strategies. And we built a demonstrator with model cars that implement CACC, so vehicles form a platoon. And we also have implemented these data injection attacks, and we use this test bed now to try out our misbehavior detection strategies beyond and reaction strategies beyond just running this in simulators. Yeah, so as I discussed, as I'm showing you, we are taking this step now from detection to reaction, and this is something where also more and more researchers look into how can automated cars react to attacks. And I think in this spectrum there are more ideas to be investigated in more detail. And this is what we are currently, or what we are still looking into in the SecForCARs project. The SecForCARs project also has a large spectrum of other topics that we investigate. For example, we look at methods and tools for safety security modeling and risk analysis. Some of these tools, like this TMT E4PT threat modeling tool for penetration testers, are open source. We are working on automated strategies for attacks and penetration testing. For example, an automated ECU security tester, attacks on radar, fuzzing frameworks for protocols like SumIP, etc. Yeah, and we are also looking at security mechanisms and concepts, how to make automated vehicles and in their internal architectures more robust. For example, secure ECU concepts, secure sensor data fusion algorithms, and of course also misbehavior detection and its integration with in-vehicle intrusion detection mechanisms. Yeah, and this research, we are now extending this research beyond the national scope in a cooperation with partners in Japan in the SAFE project, where we then join the expertise of German partners and Japanese partners towards securing automated vehicles. Yeah, this concludes my presentation, and I hope you liked it. And if you have questions, as this is an offline presentation, you are invited to either send me an email or to join a Slack discussion. So this link here will be active in the PDF that you can also download from the website. And for the next 2 weeks to come, you can reach me there and directly discuss with me about security for connected automated vehicles. Thank you for your attention and hope to see you in a discussion. Goodbye.